Good morning, good afternoon, and good evening. Welcome to our webinar, How RightScale Architects Its Databases for Worldwide Scale, HA, and DR Scenarios. In today's webinar, we'll share the data taxonomy for specific RightScale systems, give you insights on how to think through your own data taxonomy, and we'll go deeper into RightScale's distributed database architecture. So I'd like to introduce our speakers today. I have with me Rafael H. Saavedra. He's RightScale's VP of Engineering. I also have with me Josep Blanquer. He's the Chief Architect at RightScale. They've both been doing this stuff for the last 6 years at RightScale and really since the absolute beginning. So today's presentation represents the culmination of all of their efforts and learnings over the last 6 years. And with that, I'll hand it off to Josep.
Thank you, Sarah. Well, I'm going to do a brief introduction. The menu for today is basically some level setting concepts that I want to introduce because are core to the conversation that we're going to have later on. We're going to go through the data taxonomy. So we're going to go through the types of data that we have at RightScale and what type of features or what type of treatment do they need. And with that in mind, then we'll get into the storage design in basically allowing these the different pieces of the data taxonomy to be deployed according to these features in terms of scale, high availability, and DR. So one of the things that I want to do first is make sure that people understand what this webinar is about, especially when it's not. I mean, this is not a talk about the RightScale architecture. Although there is a lot of architecture that we're going to present, it's not a systems architecture. It's just a database architecture of some select systems or representative systems that we've chosen that have interesting characteristics. I'm also not going to get into data modeling, and most of what I'm going to present here is already used in production, except some of the more advanced DR features that we're going to talk in the end. So before we get into the taxonomy, I want to introduce a bit of a spoiler alert about the technologies that we have chosen to implement our data stores. In particular, we're going to use MySQL for relational data and Cassandra for anything that is NoSQL and distributed databases. We do use S3, but that's a bit more boring because it's only basically for backups and archiving. So there's three themes or three features that are going to be important in how we define and differentiate our use of MySQL or Cassandra. The first one is transactionality. Obviously, we need something with strong ACID properties. We're going to use MySQL. Cassandra, on the other end, it's really does not really provide atomicity and very little isolation, and you have to be willing to have a data store that is eventually consistent when you want to use it. At the same time, though, it's highly available, which is the second point here. It's really distributed, masterless, and highly replicated. So that's where we want to use it. We can live without those ACID properties. In terms of availability, MySQL is really not that available. You can do all kinds of master-slave setups, but at the end of the day, you will have to basically promote a slave to be a master. Any master-master setup, in my view, in my experience, is quite complicated. And there are some situations that you may want to use it, which somehow it may allow for no downtime if one of them fail, but still, it's even if you have two hosts running together, it's much less available than Cassandra. Finally, we're going to also talk a little bit about sharding because that's the way that we're going to horizontally scale part of our infrastructure in terms of accounts. So really, in this situation, we have not much help from the data stores that we've chosen. MySQL has no specific sharding tools that help you. Internally, within a single host, he does a lot of interesting things in terms of data placement, but from a data perspective, from a client perspective, really there's no help. Cassandra is underneath, uses much more of a sharding scenario in which it partitions the data by key, but again, this is only internal and is not available to the application. So now, with these three concepts, let's start taking a look at our data taxonomy. With that, I'm going to let Rafael talk about that.
Thanks very much, Josep. And after a very exciting beginning, let me just introduce a couple of concepts that are, I think, going to be valuable for the rest of the presentation. We're going to basically reference a concept that is a marketplace assets. And for some of you that are familiar with RightScale, I think you are very familiar with this concept. That is where we basically, it's like an app store when we make available write scripts and server templates so that the users can share that with the rest, either privately with other accounts or publicly to everybody else. And what is a write script and a server template? Well, these are configurations that are objects that are user-generated, private, or shared that are used to configure servers. So if you want, for example, to configure a server to act as the master in a MySQL database, well, you use a server template that basically takes care of installing all the software that you need, configuring all the different the ports, configuring also all the software that is needed. And this is done by basically executing small recipes that are called write scripts. So now you know what the marketplace assets are. Now, tags is data that is attached to resources for identification and also in terms of automation and reporting. So an example, tags are very flexible. So you can basically attach a tag to all your databases. So then if you have to execute an operation on them, it's very easy because you basically said, hey, apply these write scripts or this operational script on all the servers that are tagged with the database. Similarly, events are things that happen in the management or your deployments and applications. And that, for example, events when an instance terminates or an instance is launched, or maybe notifications or other entries. So the events are these things that are basically moved through the infrastructure and that we notify you. Now, Cloud Polling and the gateway is, well, RightScale, it's a management platform that basically works on top of the different clouds. So we need to communicate to cloud infrastructure services so to get information on behalf of our users about the state of their instances, and all that information is basically stored somewhere, so it's available to you when you basically connect to the dashboard. Now, routing probably is something that you are not familiar with because it's more of an internal infrastructure communication network that we use in order to communicate instances across the different clouds so that they can basically coordinate with each other and we can build automation on top of that. But routing data is important to distinguish it from the other one because it has a special way of handling them from the point of view of storing them in databases. And finally, monitoring data, well, most of you are more familiar with this, is all the data that the instances running on the clouds generate that allows to look at and maybe attach alerts and maybe also attach the write scripts that will execute if certain conditions happen on the instances. For example, maybe your instance may be too loaded and you may need to auto-scale. Well, all the monitoring data has to be captured so that our systems can respond to that. And you can imagine that if we manage hundreds of thousands of instances, the amount of data that they generate, it's in the gigabytes per hour or things like that. So we have to store it in a special way. Okay. Now, once I have introduced these concepts, let me give you the taxonomy of the RightScale data. And all the data that we collect in RightScale, in a way, can be classified into 5 different groups according to the properties that they present. And these 5 classes are global objects, and you can imagine what it means. It's things that have to be visible to everyone. Then we have dashboard objects, but they are not global. And these are things like, for example, the deployments, the audits, and so on. So let me go more specific about what global objects are. So global objects is, in RightScale, we have these 2 concepts of users and accounts. And user is just the ability for someone to connect to the system and have access to it. Normally, it's an email is attached to a user, and probably one of you has an email, but you may have access to multiple accounts. So accounts is a repository of resources that are managed as a unit. And for example, in a company, there may be multiple accounts representing multiple departments or multiple projects within a department. So a person who has only one user, let's say account, he may have access to many different accounts that manage resources. So in this way, users are in a way a global object because they have to be visible across all the different shards or all the different clusters, because you may want to manage resources, let's say, for an account that lives in Asia, but also you may want to switch and manage resources in an account that we see in Europe. And therefore, in order to move seamlessly from one shard or one cluster to another one, this notion of a user has to be visible globally. Similarly, if you create a new account, well, all the characteristics of an account, basically the plant that tells you all the rights that that account has, it's also something that has to be globally visible. Similarly, the multi-cloud marketplace, all these app store resources have to be a global, has to be visible globally to allow everybody from anywhere in the world to be able to download server templates and into their own accounts. Now, dashboard objects, these are resources that are managed within an account. And this is important distinction because we're going to shard horizontally based on account. So that an account, in a way, is a protection, is protected from any other account by isolating them in a way that you're only working on the concept of an account. So, and that account lives in a specific shard, so that if you do that, you don't have to move across different shards in order to do your work. And all the information that belongs to an account, like deployments, alerts, inputs for a server, or audits, or tags, or even user, belongs to the account, and is completely independent from each other. Now, as I said, we basically sit on top of cloud infrastructure services, and we need constantly to poll these services, collect information that we need to store somewhere. So this class of data is different, and we store it in a different way. Going back to the routing data that has to do with the messaging infrastructure that we build in order for instances to communicate with each other, this data also has its own characteristics. And finally, monitoring data. It's something that is produced by the instances in a massive quantity, but that is consumed by users maybe sporadically when you look at your instances and try to see what is basically the status of the different metrics and make decisions about them. Okay. So once we have these different 5 classes of objects, we can classify them based on 2 different dimensions. One dimension is which data do we need? And one concept is we need the data visible on all accounts, and we need data that is visible for a single account. So if we partition the data based on that, what we see is that global objects have to be visible across accounts. And that's going to be one classification. However, everything else that has to do in the concept of an account, that is the dashboard object that you see when you connect, or the cloud polling data that belongs to the resources of that account, or the routing data or monitoring data, that one is just isolated and only has to be visible for one account. So that's important because what it says is that we can partition the data and treat it differently by basically identifying these 2 classes of behavior. Similarly, another dimension is who uses the data, or where does the data has to be close to in order for it to be efficient. And we have 2 different concepts. One is users, either through the dashboard or through the API, need to have access to the data, or instances that are running on the cloud may need the ones that need to have access. So if we basically try to classify the different groups based on that, what we see is that we have 2 different groups. Global objects and dashboard objects have to be close to the users. However, the instance polling data from the clouds, or the routing data that instances require, or the monitoring data has to be close to the instances. Now, monitoring data is a special case because instances produce the monitoring data, but probably users consume it. But it's better to put the producer close to the data, just because for the massive amount of data that is generated. It's more efficient to do it that way. Okay. Now, if we combine these 2 dimensions, what we see is that all the data basically can be grouped into 3 different classes. Data that has to be close to users and globally accessible data. And you can imagine that that one basically requires a database that is has to satisfy these requirements. But on the other hand, we have data that has to be close to the user, but can be account shardable data. And that's basically, it's a lot of the data and makes it easy to shard based on accounts, so that we can distribute it geographically, so that users in different regions of the world can be closer to the data and also be isolated from failures in regions in which basically they don't have to be. And finally, we have also data that can be isolated on an account basis, but that is consumed by instances. And therefore, it makes sense to treat this data differently from the one that users access. Now, we're going to go deeper into that, and Joseph is going to use this information to tell you how we architect the whole RightScale to do this. Joseph?
Yeah, so basically they were slicing the data through through two different shapes, so to speak, gives us 4 quadrants. As you saw, there were only, if I go back in the slide, there were only three of these quadrants. The 4th quadrant would be basically global data that it needs to be pushed close to the instances. We don't really have that, although you can think of as routing data as being one type of that 4th quadrant. Just to keep things simple, we're going to work with these 3 different categorized pieces of data. So I'm going to build the architecture, our data architecture, with some of the example services that we have using these 4 quadrants. Actually, we're going to fill out 3 of them. The first one that I'm going to introduce is the global services. Remember that this is data that users need to be able to access, through the dashboard or through their client APIs. But it's data that it's relevant to all accounts. Like, remember, users, settings, and things like that. Well, the way we implement this global data is mostly through database, through MySQL databases. So we have many systems in here, and they're inherently very relational. That's why they're implemented in MySQL. We heavily use the master-slave replication shenanigans so that we can read from the slaves and all these things. Now, the interesting thing, I guess, that some of you guys that have dealt with this maybe you're thinking about is that, well, you just told us that MySQL is not very good at high availability, and you're trying to put your global data that needs to be accessible to all users into that sort of technology. And there's really an interesting differentiation in terms of our use case in here. What this needs to be really, really highly available is the data from a read-only perspective. So all of these data, I need to be able to read what the user password is, what the settings are, what the plan of that user and account is at all times. That must be super highly available. What is not necessarily as required to be as available is writing and changing that data. So in a sense, if we have a master-slave database in one of these services, and we need to promote the slave because there was a full master failure, these 2 minutes that might have taken us to promote the slave, maybe I could not add a new plan, or I could not change a user password. That is, for now, A-OK. If we ever needed that high availability from the point of view of the rights on this particular small piece of data, then we could move that to another technology. The interesting part is the read availability of this data. For that, what we do is we replicate that read data for read-only purposes to any other part of the system that needs it. So that is completely highly available by basically replicating it. Instead of using MySQL replication to do that, we use our own flavor of custom replication. And the main reason is because MySQL does not support getting a slave that replicates from multiple masters nicely. So we need to be able to have one single database that gets 2 streams replicated in. We need to be able to, when one of these streams breaks, resync and get back into the normal, resync back into the stream of events of one of them without having to build the database from scratch. We also like to apply several transformations when we replicate these rows, because sometimes the different pieces that receive this information may have slightly different schemas, so we may want to tweak those things in a custom way, and that's basically the main reason for which we cannot use directly the MySQL replication. Now, so this is the global data. Now, the more interesting part of the data is in this upper right quadrant, which is data that the users need to access, basically through the UI or through the API. But really, the data that they use, it's bound to their account. So account-bound data that needs to be close to the users. So there's several, there's many services that compose this, and there's 4 of them that are chosen here as representative. One of the main ones down here is the dashboard. It's probably what you're most, if you're RightScale users, that's what you're most accustomed to seeing. Anything that has to do with your UI, when you configure a server, when you change, when you create alerts, everything that you do through the dashboard. That's what this service represents. Mostly, all of this information is very relational. We need strong ACID semantics because, you know, a server has several instances, has certain alerts, it belongs to an account. This is the typical MySQL relational, well, any RDBMS relational type of database. We use MySQL for that in a heavy, again, master-slave replication. We have many slaves. We do read from the slaves in many of our processes that don't need to have transactional right semantics in there. And an interesting thing in which, by which we have designed these databases is that every single row that belongs to these databases is tagged with an account ID. So if I read any row of any table, I can see which account that row belongs to. And we'll see that that becomes very important later on for the sharding capabilities. Now, on top of this dashboard sort of service, we have many other services, and many others don't use relational databases. So let's take a look at these three examples. For example, the tags. The tag is a service, like Rafael was saying, is a very simple service that, logically speaking, relates a resource having many tags, or you can say, given this tag, what resources have that tag, right? It's kind of a two-way hash function, if you will. The tags, for example, are deployed on a Cassandra database. Basically, anything that we can simplify from a data model perspective that does not require complex searches or joins, we consider applying it on Cassandra. It's not that Cassandra cannot do certain searches, and some of them are quite powerful, but in general, it's much less flexible than any relational database. In a relational database, you can have tables, you can apply indices. After the fact, you can slice and dice and make and adapt the queries as your application evolves. With NoSQL databases, it's usually a little more strict in how you define the schema to begin with. Another interesting service is the audits. The audits is basically a service that will store interesting things that happens in your account. So there's a lot of interesting things that happen at all times in your account. When that happens, we must have a service that we can push data into. Right? When you need to save an audit, you cannot just find that the service is not available. So in that case, for the audits, we do need extremely high write availability, and that's one of the things that Cassandra shines from that perspective. Even for the ones that you're not used to it, for the most part, writes are much faster than reads in Cassandra. So that works very well for the audit entries service because we also need to push a lot of data into it. Lastly, another example of service that uses Cassandra, but in a slightly different way, is our events, our recent events notification. The little side left pane that you see in the dashboard that tells you what's happening in your account, what's been happening in your account for the last 10 minutes. So for that, we use Cassandra with the TTL, with the time to leave expiration feature they provide. So basically what we do is, like, every single thing that happened for your account or for your user, we write it into this Cassandra data store with a TTL of 10 minutes. So that gives us the ability to push as much data as we want inside that Cassandra cluster, but at the same time knowing that when I ask for the events that has happened for my account, I will only get the window of 10 last minutes of events, because automatically Cassandra will expire those rows. Okay? All these guys, like for example audits, we use S3 for archiving and and backup recovery and things like that. But for the most part, we don't do anything too weird with S3. Now let's back up for a moment and see where we were here. Right? We said that this quadrant has data that can be partitioned by account because it's only relevant to a given account, whoever is accessing the dashboard. Therefore, one can think of partitioning that into several subsystems, in which each subsystem caters to a subset of accounts. So we call those subsystems clusters. So if I expand this quadrant to see a little better what's happening, is basically what you probably are thinking. It's like we assign a set of accounts to a given cluster. So a cluster caters to n accounts. Each account will only have one home, right? An interesting thing that we can do here is that we can migrate accounts from one cluster to another. And remember that I said that every single database row that we have, Cassandra or non-Cassandra, is tagged with an account ID. So really moving an account from a data perspective, moving an account from cluster 1 to cluster 3, it's only about selecting, so to speak, all the rows with that account ID column, in moving them, inserting them into the other cluster, right? Think that these clusters are really separate from the point of view of services. Each cluster is self-contained. The only thing that they basically inject is the read-only replication data from the global service. So they're really independent. So they can really be isolated from failures from each other. We can do interesting things like some clusters running some version of the code that is a little more advanced or a little older. We can get differentiated service in some of the clusters, etc. So that's the way we partition the account partitionable data that must be user-facing.
Joseph, maybe before you move to the next slide, we can answer a couple of questions that our audience have basically sent us. One of them is, how do you handle the performance implications of multi-mastering MySQL DBs across clouds regions?
Well, we don't use multi-master replication in MySQL. It's a fairly complex thing to manage because there's not a good way to resolve conflicts. So we will see that our DR strategy sort of has two masters, but it's not really active. So the last part of the slide, you'll see what we do from a MySQL perspective across regions. But we don't directly use master-master replication.
And another one that maybe was not clear from what you have said, it says, has your application been designed to handle two different data sources and use them appropriately based upon page function?
Yes, definitely. So we have many subsystems or subservices, if you will, that will need to be accessed on every incoming request. So some of them are direct database things, some of them are REST calls to other services, some of them are external calls. So I think that that's a very typical way to do this, SaaS-based systems, definitely.
Thanks,
okay.
Joseph.
So let me go to the so we saw how we partition things based on account data. Now, an interesting thing that this is that we wanted from a taxonomy premises was that these clusters, we want to push them close to the users, right? That was the initial premise. So by having these clusters be independent from each other, we can decide where we actually deploy each of these clusters, such that I can deploy, I can basically assign a lot of accounts that are, say, Japanese, that have Japanese access into a cluster that is very close or in Japan. Right? That way we can slice that geographically from the point of view of the account access. Now, data that the instances need to access rather than the users. Well, one, we can think of doing the exact same thing. With the three example services that we presented here, well, where do we deploy these guys? So can we do the same thing of a cookie cutter replication so the instances can actually get that data close to them? And the answer is obviously yes. And we call these little sharded environments, for lack of a better word, very apparent when you think about it. We don't partition this data or the data that these services have based on the accounts. We partition them based on the data that the instances, that the clouds running, that the resources running in the cloud have. So let me expand that quadrant so it's a little clearer.
Maybe one comment here is that an account can manage multiple instances that may be running in different clouds, and that's why we make the distinction between a cluster and an island.
Right. So a given RightScale account that may live mostly in that has customers in the US East, so to speak, may actually manage instances that run in US East clouds, Japan clouds, different cloud providers, and so basically he has to have access to all these things. But the key here on this lower quadrant is that we want to have, if you take a look at these three bubbles as the three representative services that we provide, we want to push these three bubbles in cloud, right? So we want to have these services existing in any cloud, in any major cloud really, that our customers have resources running on. That way, the little green dots, which represent instances of accounts, they can communicate and then can consume these services that are within the same cloud. So that's very efficient, right? We want to push that data very close to the instances that use it. That's what this island concept is. So how do we design that from a data store perspective? So let's take a look at these three let's take a look at one of these islands and see the different representative services that we pay. First one was the polling. The polling service, as Rafael is saying, is something that needs to continually poll the cloud for changes. It needs to discover what's happening and changes this polling into a stream of events of things that have changed. We don't directly consume a stream of events from a cloud just because at this point clouds do not provide that stream of events. So we synthesize that by polling and sending deltas. Right now, that's based on MySQL, just because that's how we started 4 years ago, when we put together these specific polling systems in place. But the reality is that it's a very columnar data. So there would be, we don't use joins, and we don't use, relational databases features for this. So we could easily move this into NoSQL database. On top of it, this is very scalable because every single process of an account can be completely parallelized in polling different clouds. So that's also a good thing. It's very shardable from a cloud perspective. Another interesting service that we have here, that I chose here, is just because monitoring is a bit weird. Monitoring is just a bunch of servers that need to be able to get metrics, a lot of metrics from running instances, and store them. Store them for display purposes. When you go to the dashboard and you see the pretty graphs, that's where the metrics come from. Or we need to also compute alerts from them. So this monitoring service, in this case, it's interesting because it does not use MySQL. It does not use a NoSQL database. It just uses flat files. We have a lot of monitoring servers that basically ingest metrics and save them locally. Then we do have backups and replications to S3, but for the most part, it's just flat files, just RRD files, to be exact. So I thought that was an interesting thing to point out too, that not everything has to be uber complicated and using the latest technology. We're actually thinking about changing that into a NoSQL database, but that's a different story. The last of these services is the routing service. This is the most interesting, I think, because it's the most complex. So this one basically is also running on Cassandra, like we saw in the tax service and the events that we have in the core. The interesting thing here is that the data model is pretty simple too. Similar to the tags, you just have routing tables. You have to say, oh, for this particular target, this is where you need to go. It's kind of a hash value pair, key value pair sort of storage. So that's why it's good to use a simpler data model stored like Cassandra. The interesting thing here is that we need extremely high availability. And we need high availability not just for reads, like we wanted in the DAG service, for example, but also for writes. We need to be able to, for any instance that needs to know where to send the message, we need to very quickly tell them where. And we also, at the same time, for any new instance that comes into play, we need to be able to know where it is. So we need to be able to update the routing tables appropriately. So on top of it, from a local perspective, every island has to have all the information available to route messages to any instance of that account across clouds. Like Rafael is saying, an account could be managing instances in 10 different clouds. And any instance in any of those clouds needs to know where everybody else in that account is. So that's why you see here the connecting dotted line across the database to the Cassandra rings here that you haven't seen before. That really means that every single island has a complete copy of the data from a routing table perspective, but at the same time, they are all connected and in sync. And Cassandra understands these data center replication concepts and makes sure that every change on any of these rings is propagated accordingly to the other data centers. So the net effect here is that we can have a data store that is local reads and local writes from an island perspective, but that everybody eventually gets the memo, so to speak. But we don't have to worry about that because that's one of the main strengths of Cassandra. So let's take a look at where we are. So we said that leaving the global side, the global systems aside, we have a level of partitioning that we call clusters, in which we can push the data based on the geographical location and assigning accounts to a given cluster. So the data, when they access it, is very fast and efficient. From an instance perspective, we can also push the data that they need based on the cloud that they're running on, right? So while on top, the important thing is the different geographies. The bottom one is really the different clouds. Okay? So now let's see where we are right now in terms of isolation. So what if island N that is deployed in your private cloud goes down? The whole cloud goes down. Well, even though we may have, we'd have deployed all these services across any availability zones that you have in that cloud, if for whatever reason the whole cloud goes down, the question is, what do we do? How do we recover from that? And the interesting thing from this lower right side perspective is that there's nothing needs to be done. That needs to be done. If the whole cloud goes down, the instances running on that cloud will be down too. So there's nothing to manage. So we're basically screwed. Nothing needs to be done. Now, what happens though when you think about it? If a whole cloud where a cluster is deployed fails, that's a different story. If cluster 1 is deployed in some US East cloud, then those accounts that were served by that cluster are down. It doesn't matter that we have used 5 availability zones to replicate all the services. In the unlikely case of the whole cloud going down, those guys are not going to be available to get the service anymore. So that's where our DR strategy comes in. And this is how we approach our DR strategy. And it's actually pretty simple from a logical perspective. Really, we say that for each of the clusters we have, we're going to define pairs, well-defined pairs of clusters. So cluster 1 is going to be a pair of cluster 3. And logically speaking, we want to have a full replica of the data available for these sister clusters. Okay. So what does that mean? It means that for every master database that we have in cluster 1, we need to have an extra set of replica of the data that goes in cluster 3. And same thing the other way, right? Every single master database that we have in cluster 3, we want to have an extra replica on cluster 1. Same thing happens with the NoSQL database. We have to have that any write and any replication, any update to one of the rings in cluster 1 needs to make it into cluster 3. Interesting thing there is that from a Cassandra perspective, again, he understands, or he can understand the fact that there's 2 data centers that they need to have the same data. So we can leverage that replication, native replication, if you will, from a Cassandra data center perspective. The other master-slave replication we can do easily with the typical master-slave replication. Now, we have that. The only thing that we've done is like we have ensured that we have an extra copy of the data elsewhere in a different cloud, right? We still haven't solved the problem of how to recover if the whole cloud goes down. So let's assume that this US East cloud goes down, the whole cloud. Then what we're going to do is we want to re-enable the customers that were living in US East, in cluster 1 to be specific, to be served from cluster 3. So the first thing that one can think of is that basically say, okay, cluster 1 went down, we're going to go to cluster 3 and start basically relaunching more dashboard, more tag services, more audits, more events, and all the other services that compose RightScale, and point them to the databases that we have replicated over there. Well, that may work. Our thought is that, and it actually has happened before, that when such a major disaster happens, everybody's on the same boat. Everybody will be trying to get resources in cluster 3 exactly the same time that you are. So most likely, or it could be very possible, that you don't get to get as many resources as you want. And if that was the case, then you would not be able to serve those customers right away. Instead, what we said, we've designed our system such that when such an outage happens, we can repurpose some of basically the services that are already running in cluster 3, repoint them to the replicated databases, so as that we can already start serving some of these accounts from that new cluster. Obviously, this means that it might overload some of the systems a little bit, but we have a way to throttle it over time. So over time, we assume that we can get enough resources to get back to the normal load. So that I thought that was an interesting thing to share too, because it's not, in a panic moment, you don't really necessarily think that you're gonna have a shortage of resources, but everybody's in the same boat.
Could we say that this is in between a warm and a hot disaster recovery architecture?
Yeah, in a way, that's what it is. Yeah. Yeah, because the data's there warm, but nobody's using it. So we just have to basically repoint. It's a fast promotion, if you will, fast repointing of services to the new databases that are there, just replicating data but doing nothing other than that. And I think that's all I have in terms of the architecture. Maybe I'll hand it off to Rafael to do some conclusions.
So before the conclusions, why don't we go and try to answer a couple of questions. So one question says, within a cluster for accounts, are there more than one instance of Cassandra and MySQL, or single? For example, data X goes into Cassandra instance A, and data Y goes into Cassandra instance B.
Mm-hmm. Definitely. There are many Cassandra rings within the single cluster. That single cluster only had, I think, 4 representative services, but there are many more, right? I just picked those 2 because I thought that they had some interesting part on the data storage thing that to expose basically. But every cluster has several Cassandra rings, some of them quite big, and several MySQL databases.
Another question is how to set up SSL connections for multiple locations in and out of Amazon AWS.
For MySQL replication, I'm guessing?
It doesn't specify, but
I'm assuming that, yeah. So there's different ways that you can connect the master slave, say, across a different region. You can use the SSL, whatever it's called, native thing for the slave. You can set up an SSL certificate across the master and the slave. What we do though, because we already have tunnels open and certain firewall things in place, for this DR purposes, we actually tunnel through the replication through an SSL tunnel. We don't directly use the master connecting through SSH into the slave, but you could do that too. You just have to. It's a matter of I guess what's easier for your ops team. If you already have some tunnels, you may want to leverage that.
Okay, thanks, Jose. So in concluding, I think we have shown you how RightScale uses multiple database technologies, and we basically use MySQL, that is a relational database, and we like it because of its acid to the semantics and queryability. At the same time, in some of our services, we like to use Cassandra, and the reason is for availability and scalability. As you have seen, we use it extensively and in quite sophisticated architectural frameworks. We also present you how RightScale uses them, the different databases in different techniques, according to the properties of the data that we want to store based on availability, scalability, and also the ASIC semantics that each of each presents. And we basically show you 3 different classes of data, how we partition it. One of them is we partition based on what we call islands, and the idea is cloud proximity. That is, instances who are running on a particular cloud, they need to have all the resources from RightScale that will allow that instances to communicate with each other and to do it efficiently. Also, in terms of if a cloud is not affected by basically the failure of another cloud, well, all the instances that do not belong in the failing cloud should not be basically should continue to work without any disruption. And that's why the reason of an island makes sense. Now, in terms of scaling our system based on accounts, as we grow RightScale, we have introduced this concept of a cluster. And what we do there is that we put accounts into different clusters based on the location of the user. So, for example, if you are in Japan, as Joseph said, probably your account will live into the Japan cluster. Now, something that I think is interesting or important to mention is that your instances may be running in Japan, and you may be managing also from Japan, but not necessarily you want your instances and your account in the cluster to be in the same region. And the reason is, if there is a failure on the Japan region, well, not only your instances for your application that is mission critical will be affected, but also your ability to recover will be affected if you are managing them in the same region. So normally what we do is we suggest is that probably if your instances live in Japan, it makes sense for your account to live in Singapore because you are close enough to the Asia region. But then if something happens in Japan, then you can recover by just basically connecting to RightScale in Singapore and then relaunching and doing the disaster recovery that you have to do. And finally, we introduced the concept of cluster pair or sister sites, and it makes sense there in order to recover from a full cloud region failure. In a way, what we do is that we already have the resources in different regions because we have different RightScale systems running in these different clusters. So by just replicating across the sisters allows us to have the data ready to be, in a way, put hot when we detect any failure. And I think those are the main lessons of this talk. I hope that you found it interesting. I think I'm going to pass the mic to Sarah, who will basically give you the last messages.
Great, thanks so much, Rafael. And actually, we have a few more questions from the audience that we wanted to be able to take a moment to answer. So I'll just let Giuseppe do that for
Sure.
a couple
Maybe
minutes.
I can try to go quickly on some of them. For example, one here is, did you ever consider dedicating certain DBs for reads and others only for writes? Yes, we do that extensively with master-slave replication. We have many slaves that are read only for different reasons, like for things that require higher read performance. Another one, are you replicating data out of any of the Cassandra instances and back into MySQL? And if so, and if you are, which system is the ultimate authority of the data? We actually don't move data from Cassandra to MySQL, basically for this reason. Well, number one, we don't need it right now, but number two, then you have the issue of making sure that you can resync things correctly if something breaks. And another one, maybe, how do you route users to the correct cluster? Well, it's a combination of things. Basically, when you log in into, you can log in into any clusters that we have, or you can attempt to log in as a user into any clusters that we have, either through the dashboard or in the same way through the API. What we do is that if you try to log in with account 10, so to speak, that you have access in the user, and we see that that's not the right cluster for that account, we're going to send you a redirect into the right cluster. From a dashboard perspective, it's going to be an HTTP redirect. From an API perspective, it's going to be a redirect header as specified by our documentation. So basically, you may try to log into one place, but then we bounce you into another. One more, maybe?
Please.
One more. Okay, next one. How do you keep your product schema up to date across clusters? Well, we don't necessarily keep it up to date. One of the things that what I introduced at the beginning is that an interesting part of being able to horizontally partition across clusters is that you could have potentially some clusters at a different version level of the application. That could include slightly different schema. Now, what we don't want is to have different clusters to diverge a lot between schemas. But we do have the ability to move you from cluster A to cluster B and reconcile the differences that those schemas may have.
Yes, and one application of this property is that, for example, sometimes when we upgrade our system, we do it on a per cluster basis, and in order to minimize the effect on the users. So, for example, sometimes when we do some upgrade in the Europe cluster, for example, it may be convenient for them because may not be using it, but may not be convenient for other clusters. So we basically straddle the upgrading of the clusters, which that means that when we're doing that, the schema on the different clusters may be with a little bit difference between them. As Joseph said, we try to minimize that.
All right, thanks so much, Rafael, and thanks, Giuseppe, and thank you everyone for joining us today and sticking with us through to the end. I'm going to put a couple resources up on the screen right now, some interesting next steps for you. I'd also like to announce RightScale Compute. It's our next big RightScale community event. It's in the end of April in San Francisco, and this is your opportunity to meet Giuseppe and Rafael. Many others from the RightScale team will also be there. We're excited to announce that Rackspace is our platinum sponsor, and we've got Google, Apica, Equinix, and others as gold sponsors as well, so that's very exciting. So check that out, rightscalecompute.com. Thanks again for joining us, and have a great day.